I'm from the University of Manchester, and I'm going to talk about work I've been doing investigating the key sources of and processes contributing to particulate pollution in Beijing. So, to firstly give an overview of where particulates or aerosols are important in the atmosphere. So, we have loads of different VOCs that are released either from things that we do, so anthropogenic processes, or from plants. So you can see there, it's very complicated. If I can figure out how to do it. Okay, so yeah, you can see there from the trees, they're releasing these isoprenes and terpenes, and then you've got these anthropogenic processes that either produce aerosol directly, or that release these VOCs that are oxidized in the atmosphere and then end up creating species that can partition into the aerosol phase. So I've highlighted these oxidation things because they're the bits that I'm interested in. So the problem in Beijing. At a very basic level, the problem is rapid industrialization, and in terms of the meteorology, that controls a lot of the pollution in Beijing, especially in the winter time where there's very low wind speeds and conditions can get very stagnant. And then in terms of the topography, there is a lot of industry to the south and there are mountains to the north. So like air masses can get trapped, very polluted air masses can get trapped in Beijing. If we look a little bit further, there are slight little differences that we're discovering now in terms of fuel composition, cooking habits, and residential burning. There burn lots of different random things there that we wouldn't really expect. But all these things are interlinked. So that's where it becomes slightly more complex. And because of that, we're part of this Air Pollution and Human Health project. And that's an integrated study of the emissions sources and air pollution processes in Beijing. Now, as part of that, we were involved in two different field campaigns, one in November, December 2016, and one in June 2017. So our piece of the problem, or my piece of the problem, we've got all these different VOCs being released from these different processes. So from combustion, plant emissions, cooking, and burning. And these are oxidized in the atmosphere, loads of chemistry happens, and then that creates these semi-volatile gases. Now, those semi-volatile gases can actually partition into the particle phase, so they can exist as sort of gases or particles, or a sort of equilibrium between the two. Now, that's the bit of the problem that I'm interested in, these semi-volatile gases and the aerosol. But this is slightly more complex because you can actually get the semi-volatile gases from these processes, and there are loads of these unknown sources. They're not all very well defined. So how do we investigate this in the field? So the instrument I use to do this is a time-of-flight chemical ionization mass spectrometer. Now, how that works is we sample ambient air when we're in the field, and we attach an iodide to every compound that we measure, or we try to attach an iodide to it. And that's how we detect it. So that gives it a charge, and then it's able to be detected in the mass spectrometer. Now, there are different types of mass spec. I'm sure some of you will have worked with them before. Because this is chemical ionization, it's a soft ionization technique, so we retain molecular level information. So we actually detect the specific ions or the specific compounds rather than fragments of them. Now, I was saying that I care about both the semi-volatile gases and the particles. To kind of measure both of them simultaneously, we have a special inlet, which is this FIGAERO filter inlet for gases and aerosols. Now, how that works is when we're sampling in gas phase, we're actually collecting particles onto a filter. After a defined period of time, we automatically move that filter to desorb those particles into the instrument, so then we're actually detecting what was in the aerosol phase over that collected period of time. And as that happens, as you can see on this bottom one, when it switches from green to red, the composition of that actual mass spectrum is changing completely because we're measuring the particle phase, not the gas phase. So there's a lot of data. We've got this huge mass spec, which is collected over a time series. And each species we're measuring tends to vary in time. So this is the diurnal variation of them, so how they're varying throughout the day. Each peak in there varies slightly differently from each other. So how can we find some common behavior between these thousands of unique ions? So you can either do this in terms of a bottoms-up approach and actually manually identify each individual ion and then try and group them together, either using some stuff we already know from literature in terms of reaction pathways in the atmosphere and things like that, or the approach which I'm going to talk about today, positive matrix factorization. So I will give you guys an overview of what that approach does. So we have a mass spectrum which is recorded at each point in time, and that gives us a matrix. So we can see each m over z over a specific time period. And that can actually be, so if you input this into this matrix factorization method, you can represent that ambient spectrum in terms of different unique source profiles. And you'll get some residual that you can't really explain. So it groups things by their behavior, so how they're behaving over time during what you've measured. So here's just a sample of what I've applied that to. So what you get is, so you have your ambient mass spectrum, and I've split, and this PMF has split that up into different factors. So these plus a residual will sum up to what I've actually measured. Okay, so here's some random names I've assigned to them. Well, not completely random. So the OOA is oxidized organic aerosol. So this is what I've measured in the particle phase. So bearing in mind we're measuring both gas and particle, I've kind of taken a subsection of the data for what I'm talking about here. So some of these processes come out quite nicely in this matrix factorization method. So I can see some kind of biomass burning signatures and some cooking related signatures, but then a lot of stuff falls into this oxidized organic aerosol blanket category with loads of different numbers. We can also see how these, so instead of looking at how the individual factors vary over time, individual species vary over time, we can look at how the factors vary over time. So you can see some of these are sort of peaking in the afternoon through these secondary processes when we've got sort of high ozone and high photochemistry happening at those times. And we've got some nighttime things with sort of this nitrate chemistry that reacts with some plant emissions. But the problem that we've got here is that we've still got all of these oxidized organic aerosols bulked together. So this is still too complex. So I went to other people who were working as part of this campaign and said, okay, you're measuring the VOCs. Bear in mind I said my part of the problem is these semi-volatiles and the particles. So what exactly are you measuring? So they were measuring a lot of these aromatic species. And these aromatics are very different to what have been measured elsewhere. So for example, when they've done measurements in London and things like that. And it's these substituted benzenes which seem to be particularly interesting. So I did some experiments which are actually simulating those under lab conditions. So instead of seeing everything as a giant soup of oxidized products, I'm seeing what the particles look like from all of these different precursors individually. And the aim is then, so I've got my positive matrix factorization, which doesn't completely resolve all these different sources and processes. And then I've got these single VOC experiments. So I can actually bring those together in a different technique, which is very similar to the PMF I've just described. But in PMF, you give it no a priori information. You don't tell it that you know anything. But in this technique, I'm going to say, hey, I know what the aerosol from trimethylbenzene should look like. So constrain that, and then figure out the rest in a PMF type approach. So hopefully that'll help me figure out this problem a little better, and then I need to apply it to the other data sets. Yeah, thanks for listening. Any questions?